Okay, Misha, you can start.
Yeah.
Thank you.
So
Thank you.
thank you very much, Antonia, for organizing this and for allowing me to speak slightly longer than everyone else because I'm usually too talkative. Um, and you asked to kind of introduce ourselves a little bit. And actually, this particular talk will be closely related to my kind of professional biography. But most importantly, you do not choose times when you live, and I was lucky. My first international conference was in 1990. Uh, when I still worked in the former Soviet Union, which was not former at that time, at the Yofa Institute. And my first conference was nanostructures and superlattices in Berlin, at the days when the wall was destroyed. And I walked through the ruins of the Berlin Wall, through Brandenburg gates from East Berlin to West Berlin, and I thought that this would be our future life. And 32 years ago precisely, and it is a little bit different from that, but that time defined all my life. In 92, I left Soviet Union. Actually, it became Russia a few months before that, and moved to Salt Lake City to the University of Utah, where I worked with Dan Mattis, a famous theorist, a student of Bardeen, and Emmanuel Rashba, who will appear in this talk. The famous Rashba effect, the basis of spintronics. Then I moved here in the United Kingdom with a short spell in Edinburgh. I ended up in Exeter, a place on that map. Yes, you can see a map of the United Kingdom. We are in the very southwest, and despite of the palm trees on this picture, it is currently 15 degrees and light rain. So it is not a very tropical location, but quite comfortable, probably for those of you who are struggling with the heat at the moment. Actually, that story of momentum alignment comes from my original work at the Yofa Institute with another famous semiconductor scientist, which became famous in the second half of the 20th century, Perel, who was I had to do 2 PhDs, my first PhD supervisor, and it was on that alignment phenomena. It is an educational lecture, so I will explain what it is in normal, not in nanostructures and not in terahertz, but in traditional conventional semiconductors. That will be the start of the story. So it started in 1976 when, most of the people in the room have not yet been, not in the room, I mean, in your rooms, were not yet been born, with experiment. Yes, with experiment of Zakharchenia, Zemsky and Mirlin, who had a very good spectrometer, very sensitive one, and a laser with quite a few wavelengths, not tunable at that time. So what they did, they shined at a bulk gallium arsenide, C5 semiconductor, the basis of better lasers later on, the most known kind of semiconductor. Why did I write it? Semicondutors. It was a translation into Portuguese. I think that is not a misprint. It is just the use of Portuguese language for the original PowerPoint. Hopefully, it will be corrected into English in other slides. So what happened? They shined high above the band gap. And what they saw was very bright age luminescence, it was p-doped gallium arsenide, so it was luminescence of photoexcited electrons from the band age down to acceptor level. Yes, very bright. But they had a good old spectrometer and they measured hot luminescence, which means very weak glowing at higher frequencies. And what they did, they worked at that time following Clampel and others in France on studying optical orientations, looking at exciting things with circularly polarized light and checking the polarization of luminescence. But then there they decided not to put a quarter wave plate, but look at naturally linearly polarized light from their laser and measure linear polarization of luminescence. And of course, the brightest age luminescence was completely unpolarized. But the hot one, yes, the one at very weak glowing at high energies, it was linearly polarized. And this polarization was decreasing with the decrease of the frequency, yes, with increase of the wavelengths. So they ran to the best known theorist in the building at the time, Vladimir Perel, and asked him to explain what happens. And that is what they published in Jet Flatters in 1976. And immediately thereafter, in the same volume, no, it was not, it was a theoretical paper in the full jet. It is like PhysRef letters and PhysRef in Russia. So in the same year, very quickly, the theorist explained this effect. And it is a simple effect. Yes, you don't need even Maxwell equations, but you need to understand the band structure of semiconductors. And if you look at this band structure of semiconductors, you more or less know that in 3-5 semiconductors like gallium arsenide, your holes, yes, holes, come from states with angular momentum 1, or actually 3/2 if you take into account spin. So these are kind of p states, p atomic states, and the electrons are in s states. So the selection rule, you just take your dipole and you, to calculate probability, you use Fermi-Golden rule, you calculate matrix element squared, so you enclose your x plus iy function, this kind of p-type functions of the holes, and s function, and this x plus iy are, Bloch, the symmetry of the Bloch function of heavy holes. Yes, in that previous picture, there were, this is complex valence band structures. There are heavy holes, light holes, spin split holes. But if you do take the simplest heavy holes, then you can see that your dipole, yes, have to make a transition, has to be, this dipole D vector should be either along x or y direction. But what does it have to do to momentum? Actually, it has everything to do in momentum. Because what are these x and y and z near the band age of a semiconductor, where you neglect this crystallographic symmetry, but just write this spherical type of Latinger Hamiltonian? What are x and y, and how do you choose z? Actually, this z is precisely the momentum, the direction of z can be chosen as the direction of the movement of your particles. So if you look at this top formula above, you can see that if your particle, if your particle moved along z, it needs to have, if momentum is along z, that it only be created if your light yeah, this D, this E, yes, E is polarization vector of the light, is along normal direction to the Z. So it is along X or Y. So what happens is the following. If you shine linearly polarized light, your electrons, which are created together with heavy holes, move mostly normal to the polarization plane of the light. They make this figure of 8. Actually, it is rotated figure of 8, which is all the momenta are normal to the polarization plane. If you create, however, a light hole, the light hole likes to move along E, along the polarization plane, in the polarization plane of the light. Yeah, so it was not, if you know well your band structure, it was not difficult to explain this effect. Yes, that's why the papers came so quickly. So quite a few years passed, 15 years actually, exactly, and I became a PhD student, and Perel, who was my supervisor at the Yofa Institute, gave me a problem to do the same, because in 15 years everyone started to move towards quantum wells, yes. And nanostructures, that was the main difference, and people started to measure this phenomena in quantum wells. And what experimentalists discovered was that actually in quantum wells, this alignment degree, that anisotropy of the distribution, momentum distribution of photoexcited carriers became in the instant of photocreation, started to strongly became on the excitation energy. Actually, the closer you go to the band gap, yes, the smaller is the photon energy kind of above your band gap, the less your electrons are aligned. And the reason is clear, because when you look at the quantum well, you in fact, when you look at quantum well, you in fact have momentum in one direction already from the very beginning, because your particle is quantized. It moves effectively normal to the quantum well. So the effect depends on the ratio between in-plane momentum, everything that you created by the excess of your photon energy above the band gap, and that momentum, which is quantized momentum of the motion, which is already because of the confinement. Okay, so we did that, was more or less big part of my first PhD. We did a comprehensive analysis, and we showed, which came even into some quite popular textbook. What else we discovered, that in 2D it is extremely important that with increasing the energy, the picture became strongly anisotropic in plane. Yes, that there is not only that spherical model not enough, and that it is important when you go to higher energies, the crystal axis become important. Yes, that is called trigonal warping effect, or warping effect. Actually, it's not trigonal. Trigonal, it is graphene. It's called valence band warping, which means that equi-energy surface becomes not a circle, yes, for holes, but has a complicated shape. Okay, so another feature in this picture was that this alignment parameter has a different sign, yes, for transitions from light hole and heavy holes, but that is natural, because if you remember in the previous pictures, the alignment, yes, this anisotropy of the momentum distribution also dependent on the type of holes we're dealing with. What was extracted there historically from this hot photoluminescence data, they saw, for example, phonon replicas. Yes, when they created hot electron, then it was relaxing down, yes, going to the bottom of the band, and it relaxed in steps. Yes, the steps, separation between steps corresponded to the energy of the optical phonon. And what they saw, that polarization in this each steps, yes, was decreasing. Actually, the same effect, of course, happened in quantum wells. And for example, people extracted, there was a question, what is the main mechanism of relaxation of two-dimensional electrons in hot electrons in gallium arsenide quantum well? And these experiments in these phonon replicas and decreasing of polarization degree of this, because you understand, you created anisotropic distribution, it remains slightly anisotropic until you completely relaxed, and this anisotropy reflects in the linear polarization of luminescence. So what happened by making these measurements, people understood that the main mechanism of relaxation was scattering on bulk Fröhlich phonons, yes, bulk polar optical phonons. Okay, now we move to 21st century, and its first decade was crowned by, of course, graphene, which is still a very popular material and a subject of research of many of us. And by the way, plasmonics in graphene, of course, is very hot topic, because there you can change the density concentration with a bottom gap. And as you saw from the previous talk, everything in plasmon frequency depends on this carrier concentration. So what do we know about graphene? Why did it got the Nobel Prize? It's a plethora of wonderful quantum mechanical phenomena reflecting this Dirac spectrum, this unconventional quantum Hall effect and Klein paradox and Valleytronics and so on and so forth. From optics, the general public, not too general, you should know definitely this universal absorption, yes? That a single sheet of graphene, if you do not put it in special conditions on kind of into waveguide and or cavity and things like that, it will just absorb 2.3% of light, which is a combination of world constants. And you can derive this easily from either Kuba formula or just the same way as we treated selection, Fermi golden rule in quantum mechanics. That's what we know. But actually, what is nice about graphene that, it suppresses backscattering. It's good for contact. It's good for transparent displays. But the promise of digital electronics based on graphene never happened. Why? Because of Klein tunneling. Because when electron in graphene impinge normally on the barrier, yes, when it comes towards any barrier, I put a top gate here on the scheme, and my electron comes normal to the barrier, it does not reflect. Yes, it goes through with transparency 1. So whatever voltage I apply to this top gate, I cannot close my transistor. Yes, so I cannot get a zero in graphene transistor. I can do interesting things, narrowing the channels, but it will spoil my yes, it will spoil my high conductivity in on state. I can do something with frequency, but roughly speaking, graphene with all its trills is rubbish for digital electronics. So when I started to look into graphene in around 2007 or 8, at the time, by the way, of PhD of another professor and member of Terasa consortium, Richard Hartman, who you saw from the first page, is a co-author of all this work. I came with a thought that maybe if I can steer, if we can control the angle at which our electron comes to this barrier, yes, because everything depends on this angle. Maybe I will be able to modify photocurrent. But how can you steer electron? And we decided to check with Richard what happens if we excite graphene with linearly polarized light. And we did exactly the same calculation, which led to 2.3, but did not integrate over all angles. And what we discovered was that graphene satisfies exactly, if you look at this distribution, this figure of 8, apart from the fact that it is not rotating in space, but in 2D, it has 100% alignment. So if I shine with the light polarized along this direction, my electron like to go normal to the plane, and none of them go along the polarization plane. If I rotate my polarization plane, my electrons will go in this direction. Yes? Actually, this is the rate of creation of electrons, of photoelectrons, and it is proportional to sine square between the angle between my polarization plane or vector of polarization and q, my moment of my electrons. Why do I have these dotted lines? Because graphene, as you saw previously, yes, it has two non-equivalent values, which will be important for the later, and both of them give exactly the same contribution in this distribution function of photo-created electrons. So you should understand this diagram. Every point on this blue curve corresponds to a probability of electron going at a particular angle, which I count from this x-axis. Yes, so it is just a polar plot dependency of the angle of this rate of photocreation of particles with given momentum with this phi q. Phi q is the angle at which my photo-excited electrons move, yes, before any relaxation. Okay, so why do I write conical approximation here? Because I'm sitting at the moment very close to this Dirac cone, which is absolutely isotropic. But you can see that if I go higher in energy, yes, there is no cone. There is something like cupola. And there are triangles at other energies. And you saw from my work on quantum wells that warping, this dependence of energy on equi-energy surface on angle is important. So that is what we did later. We looked at what happens when you introduce trigonal warping, which means if you take into account that your equi-energy surfaces are not circles, yes, they are circles in the middle, but they are almost like triangles, yeah. And also this blue, green, and red lines, they show actually contribution to the momentum distribution function from two different values. So interesting, isn't it? So my blue line is the total distribution of photo-excited carriers, but actually it is a sum of the carriers originated from one valley, one key point, and another key point. And as you can see, they are actually, this figure of 8 is a combination of two fishes. Yes, one tail is up and another tail is down. So if you put in linearly polarized light, it looks like carriers from two different valleys go to two different sides of your sample or sides of your light spot. And that more or less the result which we obtained around 2007, 2008 and called it optovalleytronics. Yes, we create carriers from specially separate carriers from two valleys with the help of linearly polarized light. Okay. If you add, you can see a perfectly symmetric distribution. So it's important to look at both valleys. Otherwise, it will be you shine linearly polarized light. You do not apply any voltage or any anisotropy, and you will have preferential total current. Yes, which contradicts symmetry or any common sense. There is no total current if you take into account both valleys. So valleys are important. Okay, so that is a trivial calculation for graphene for difference. This valley polarization is the difference of the particles in K valley and K prime valley divided by the sum of them, and you can see that it changes sign specially in real space. Yes, special separation of valleys. Okay, how it's a lecture, so I will not kind of hide how you calculate it and why it happens. Yes, so far I just postulated that the distribution will be anisotropic, but it is actually very, very easy to see. Yes, how do you see it? If you just do your standard tight binding model and expand everything near K point, yes, it's easiest to see near the Dirac, in the Dirac cone. That is two valleys, one looks like this and the other looks like that. The difference is only the sign here, yes, minus or plus. And you calculate matrix element of velocity. You can do it by different ways. It is to be on a safe side. The best way is to consider velocity operator as a commutator with your Hamiltonian, but it's for the cone, it is very clear and easy to understand. First, I do it without formula and try to explain in the language of pseudospin. So when you create optically your electron and hole in graphene, yes, they have different pseudospin. Because pseudospin related to the slope of your dispersion. Here it is to the right, and here it is to the left. Electric field cannot flip pseudospin. Yes. So when your electric field is along your momentum, yes, when you create an electron with a momentum along electric field, it cannot happen because your hole has to have a pseudospin which is opposite. Yeah, your electron which was taken from the valence band had an opposite pseudospin, and electric field does not flip it. Yes, it's the same as Klein tunneling. Potential V does not change. You can go through. You cannot get back. Yes, you cannot. You are on the line which going forward. You cannot. You were here. Your electron was going to the left, and it cannot go to the right with the help of electric field or a barrier. However, when your electric field is normal to the plane, yes, there is no conservation. Nothing is conserved on the vector of electric field, but things are conserved. It's okay. There is a probability of you are allowed to flip the spin. But it is easier, much easier to do it with just looking at the Hamiltonian and its perturbation. That is a total Hamiltonian in the presence of light. Yes. So you add minimal coupling, yes, Px plus E over C in Gauss, or E vector potential, and Py has E vector potential added to Y component. In linearly polarized light, you have either AY or AX. Okay, so if I split between my original Hamiltonian, so original Hamiltonian, yeah, so original Hamiltonian, for example, if I move along X direction only, yes, if I move along X direction only, if my particle is created in X direction, then my, yeah, that's my original Hamiltonian. It has this matrix O1, 1, O in X, and 0, minus 1 in Y direction. And then I look at my perturbation. Yes, my perturbation has exactly the same form with AX, has exactly the same form as my H naught. Yes, it's just the constant is different. But you know that eigenvectors of these two exactly the same shape Hamiltonians are exactly the same, and they are always orthogonal to each other. So the perturbation, which looks exactly like your original Hamiltonian, does not cause transition. So if I have motion along X direction only, then my perturbation only AY place allows me transition. Or if I move along Y direction only, then only AX allows me a transition, which immediately tells you that your momentum is always preferably normal to the polarization vector of your light. Okay, what can be measured for graphene? For graphene, we can measure, for example, phonon replicas and find out the dominant mechanism of the relaxation. You can measure relaxation times by depolarization of this hot luminescence as a magnetic field. What is important for graphene? That there is no band gap, yes? So this alignment is 100% alignment always. Okay? So we calculated in Richard's dissertation various things there, and that is quite actually a long old work. Richard, who is now the full member of our consortium, got his PhD in 2010, and it came out also as a book. I was supposed to show, I have it paperback copy, the year later, and everything that I said so far was a part of this book. There were certain experimental observations, but I would rather move on with more recent stuff. Yes. So what happens in gapped graphenes or extremely popular dichalcogenides, which have band gap, and what is known is a completely different story, isn't it? They know that when they excite with circularly polarized light, they get different value occupied. But there is nothing known about linear. Linear seems to be equal occupation. And for graphene, circular doesn't matter. If you shine circularly polarized light, both values occupy completely equivalently. So what happens? What changes the story if you have a graphene with a gap? That's what happens, yes? You remember in the previous Hamiltonian, you have 0 instead of plus minus delta, yeah? And now it is delta, which is related to the band gap. So when your Q is here, your unperturbed Hamiltonian has the shape of just 1 minus 1. So it is a completely different shape. And your perturbation, of course, your A will be staying where this Qx and Qy's are staying in our values. So the selection rules change completely. At the same time, if you look here, you think, oh, but if I excite high above this gap, yes, then this delta will be negligible comparing to my off-diagonal terms. So I should recover my Graphian answers. And actually, this is something that people studying dichalcogenides do not understand. Yes, everything about dichalcogenides is about excitons. But excitons, as you know, are compact entities. Momentum is not a good quantum number. And they are combinations of many states with many momenta. So what they think of admixture of the values and things like that, it is just when they cannot get 100% circular polarization. It is just the consequence of this kind of circular polarization rule to become frequency dependent, exactly in the same manner as they became in quantum wells. Yes, but with the role of this momentum normal to the quantum well played by this band gap delta. Okay, so this is what happens. First of all, when you go high in energy, your linear polarization starts to play the role. And when you go very high in energy, even in the conical kind of circular isotropic assumption for the spectrum, your circularly polarized light, which gives you 100% right-hand side polarization for K valley and left-hand side polarization for K prime valley, both polarization merge when the excess of the photon energy is several times your band gap, which is difficult for dichalcogenides, but very easy for narrow gap graphene-like materials like phosphorium, for example, or graphene on barium nitride substrates. So actually, if I take minus alpha naught, this alignment parameter, and plot it for gapped graphene, you can see that when K is, say, 8 times the band gap divided by HV Fermi, you have total alignment. And it reminds, actually, it is minus alpha naught. It exactly reminds this bottom curve for gallium arsenide. Okay, so what happens in gap graphene? You have strong alignment when you have very high excitation energy, and you have weaker alignment when the excitation energy is small, and you can read it all in archive. So the circular polarization also, if you excite very high, then the selection rule of different circular polarization for values doesn't work. Okay. So if it happens, so it means that if I excite, if I take into account trigonal warping and excite high, then it means that I not only in gap graphene, I can actually detect this valley separation. Yes, because H state, recombination from the H state me immediately tells me which valley I am coming from. So if I have graphene with a gap, then by measuring circular polarization at different ages of the light spot, I will definitely tell how much of electrons from each valley I got at different sides of the sample. So valley degree of freedom, and it is extremely important for new kind of quantum computing applications, can be measured, and it is another quantum number similar but different to spin, which you can separate, similar to the spin Hall effect. You can introduce this optical valley Hall effect. So that is our proposal for the measurements. Actually, people did not do the measurements, but they did it in numerics. They did not associate it. They assume that it relates to spin orbit coupling, but as you saw, there is nothing to do with spin. Okay, now it comes to Rashba, which was a supervisor of my second PhD. That is a slide from Wikipedia, actually, from the Wikipedia description of Rashba effect, and I looked at the picture and I kind of recognized it. Looked into my picture collection and discovered that the people cut off here was actually myself with a lot of hair. Yes, and to the left, that is Fyodor Kusmartsev, the head of the new Khalifa node of our Terasa project. And that was in 2005. Rashba will be 95 this October. He was awarded the main American prize for condensed matter, was just awarded, and he is still alive and very much interested in science. So this Rashba effect gave rise to, which is described by this famous Rashba Hamiltonian in blue box, gave rise to data dust spin transition and the whole field of spintronics. So what happens if you added Rashba term to graphene Hamiltonian? Actually, what you see is huge trigonal warping at very low energies. So you do not need to go to huge energies and see warping due to Rashba term, which makes the following. You can add it to graphene Hamiltonian by just assuming that when your electron jumps from one side to another, yes, in graphene, it can also spin flip. So taking into account this effect gives you very strong momentum alignment, separation of values at very low energy. I know I have 5 minutes, and it is exactly 2 minutes is exactly what I need, and
perfect
6 minutes for questions. What I'm trying to say is that actually you do not need to take 5 EG or huge excitation frequency to see this warping. Rashba, which is controlled, imagine that you put your graphene on a substrate and have a gear, the Rashba turn is controlled by external electric field. Yes, you can control it, and you can control your degree of valley separation. Yes, again, green carriers are from K prime valley and red carriers are from K valley, and they go to different directions. Actually, at high energy, Rashba is also important, but it is much weaker. And it actually suppresses slightly. It goes in opposite way than valleytronics due to normal warping. But it is, I mean, they do not kill each other exactly. Okay, so remember, we are in Terasa network. And my last minute is to tell that it is all, that phenomena is actually of direct consequence for one of the work packages in Terasa. Namely, we discussed selection rules in carbon nanotubes and graphene nanoribbons. And what we discovered with Richard as well, yes, some time ago, was that this curvature effect in nanotubes or age effect in nanoribbon, they allow very strong optical transition across a tiny gap of these narrow band structures. And actually it has to do everything with alignment. Namely, selection rules say that to excite electron in a nanotube, you need to have polarization of light along the tube. But then it contradicts, it completely contradicts to the alignment concept, because electric field along that electric field does not create electrons moving along the field. Yes, optical transition rules say it has to move normal to the field. But actually the age effect and or curvature effect is exactly what creates a normal momentum. Yes, effectively it is little delta. Little delta similar to gap graphene. This little delta allows very narrow part of the spectrum when your optical transition is totally allowed and quickly becomes forbidden. That's it. So it resulted to the terahertz generation scheme when you create carriers optically and there is strong age luminescence from the age. And this is my summary, and time probably for one question if Antonio allows, or maybe there will be no question. So the summary is that you have to look deeper. Yes, 2.3% is not enough. You need to look at the distribution of the carrier distribution in real space and the momentum space. And there is a plethora of new physical phenomena which are defined by this anisotropic distribution.
Okay, Misha.